All right, people, here's your review, and you can do this review along with me. I'm not going to make it an ed puzzle. You have a lot of ed puzzles, so I try not to ed puzzle everything, even though I think they're awesome. Tomorrow's test, what do you need to know? Well, one, you need to know all these shapes except for this one. So I'll give you formulas, and you'll need to draw Lewis structures, and then most of them you'll have to label with one of these shapes. Like I said, not this one. Another thing on there that you've had from me are intermolecular forces and intramolecular forces. Now, I've talked to you about intramolecular forces, and we've talked about hybrid bonds and the hybridized orbitals of carbon. That's definitely on the test. But I haven't, this semester in person like this, given you any instruction rather than just a separate video from last semester in a worksheet on intermolecular forces. So I'm going to throw that into this video as well. So watch if you want to play it at a quicker speed. That's fine. Here we go. An example would be, hey, I'll say, hey, draw me the Lewis structure for hydrogen fluoride. Or, no. All right, hydrogen fluoride. Boom. That's got to be a linear molecule. There's no other shape. You'll need to have all the 3 unbound pairs. You know that's linear. What else about this thing? What else about it being linear? It's also polar, right? So this is linear. It's polar. It's got 2 different ends, and then you can just label that bond right there if you wanted to as a sigma bond, and you'd be done. That'd be all the stuff you could do with it. I feel like I need to take a break before I do more of the shapes and talk to you about intermolecular forces. There's 3 different types. First type is London dispersion, okay, and they're very weak. And London dispersion forces are really just forces that we know exist because we can make liquids out of gases under pressure. Like if we had an oxygen, I'm going to draw the oxygen molecule up and down like this. If we had an oxygen molecule, O2 here, oxygen at this temperature and pressure in the room is a gas, obviously. And the molecules have no attraction to each other. That's how gases work. But if we put them in a super pressurized container, basically shoved so many of them in there that they were forced together. As they were forced together, some of these electrons that repel each other would literally be pushed out of the way, allowing these 2 things that don't want to connect to actually make a very weak bond. That weak bond is due to London dispersion forces. And as soon as you take the pressure off of it, it'll break apart and turn back into a gas. And you know this happens. You know that propane in a tank is liquid, and as soon as you turn the valve, it shoots out gas. So London dispersion forces are the weakest. Okay, and then the next type of force I'd like to talk to you about is dipole forces. Now, let's say we had PF3, phosphorus trifluoride. Okay, now you could draw that. That would be a trigonal pyramidal shape, and the reason is phosphorus would have 2 leftover valence electrons. We'd have all these bad boys right here. And we know these would all be sigma bonds. Okay. Now, if we had phosphorus trifluoride in this trigonal pyramidal shape, there's never just one phosphorus trifluoride. If phosphorus trifluoride were a solid or a liquid, how would it be stuck together? Well, the top of one phosphorus trifluoride would stick to the bottom of the other. And the reason it would do that is because one end would be positive and the other end would be negative. Like the phosphorus, I would consider that the positive end, and the fluorine, that would be the negative end. So the positive side of this molecule would stick to the negative side of this one. And they stick together kind of like magnets because they're polar. They're polar shapes. So the two different poles, the positive and the negative of the different shapes, stick together. This is called dipole forces. These are dipole intermolecular forces, and they're fairly strong. All right, let's keep rolling with our intermolecular forces. What if I drew a different one? What if I drew, give me a second here. How about ammonia? Ammonia. NH3 is also, guess what? Also a polar molecule. All right? These guys don't have any leftover valence electrons. Sigma, sigma, sigma. Trigonal pyramidal. It's polar. It's got a positive end and a negative end. All right? With hydrogen, I actually don't, off the top of my head, I'm not sure it's going to be positive or negative, but check this out. It would stick to the other one like this, right? Okay, so this, I'm thinking nitrogen would probably be the positive end of this one. Hydrogen would be no, nitrogen would be the negative end of this one. And you're not going to have to label ends as positive or negative, all right? And hydrogen would be the positive end. So this nitrogen and this hydrogen from two different molecules would stick together. And you're like, aha, that's a dipole-dipole connection. It's not, because the strongest dipole-dipole connections are called hydrogen bonds. Okay? Hydrogen bonds, or hydrogen bonding. And that means that a hydrogen on one molecule is connected to either a fluorine, an oxygen, or a nitrogen on another molecule. And that bond there is very strong. So the way you can remember if two molecules, two polar molecules are stuck together by hydrogen bonding is remember this really quick saying. Hydrogen just wants to have fun. That's pretty good. That's pretty funny. All right. So that's my little review of the forces. I'm still going to stick with the shapes, though. In case you haven't noticed, we've done a linear shape, and we've done two trigonal pyramidal shapes. I would ask you about this shape right here, one that I ask about a lot, like aluminum chloride. And that actually looks like this. And I bet you know why, most of you. This one's actually trigonal planar. And if you don't know why it's trigonal planar, let's take a look at the aluminum Bohr model. See, aluminum only started out with 1, 2, 3 valence electrons. So those three, boom, 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 are already accounted for, and there's no extra unbound pairs of electrons here. If this was a nitrogen in the middle, then it would have more valence electrons, right? It would have 2 more valence electrons, and that would change the shape of the molecule. So this one right here is actually 2-dimensional, and it's trigonal planar. And since it's trigonal planar, if we looked at it, we would see that it's non-polar because every end is the same. And yeah, we could label all these as sigma if you wanted to. I'm only going to go over one more shape because we're trying to go pretty quickly. How about this? How about we do, we'll go ahead and do us a methane, carbon tetrahydride. That shape ends up being like this. It is obviously nonpolar. It would actually be 3-dimensional though, because all of these hydrogens are staying as far away from each other as they can. So you end up with this, this molecule that looks like a jack, almost like a little jack when you're playing jacks, the little figures. And it doesn't lay flat. It's 3D. It pops up. This is tetrahedral. Now, let's go one step further. Sigma, 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 sigma. Okay. So if we were looking at these sigma bonds, what would the hybridization of this carbon be? It would start out 1s to 2s to 2, 2p, 2. That's it originally. But now we see we have 1, 2, 3, 4 sigma bonds. Now a sigma bond is a combination of the 2s and 2p orbitals. So we start with 1s, up, down. That's always the same. Now we have sp. 1, 2, 3, 4. 1, 2, 3, 4. Now we have all of the electrons accounted for, and this would be called sp3 bonded, because the first arrow is the s, and then we have p and p and p. You can never have sp4 because there's only 3 different types of p orbitals, right? Let's do one more. Let's do one more Lewis structure. What if, and I'll ask you to do one of these on the test, maybe 1 or 2 at the end. What if I ask you to draw one that kind of wasn't the shapes that we're used to, like, how about CF2S, all right? What if we had CF2S, okay? First of all, which one of these is the biggest atom out of all these? Carbon. So carbon's going to be in the middle. Hint, hint, carbon's always in the middle. The F2 right here, bam, bam. I like that. And then poop, poop. That S needs 2. Everybody's happy. 1, 2, 3, 4, 5, 6. This thing's polar. Maybe I would ask you that, okay? But you can't name the shape. But you can label all the bonds sigma, 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 pi, and then show me the hybridized orbitals for carbon, which would be 1s2 sp. So sp2, because remember that's an s, p, p. And then there's one left over that would still be up here, 2p. There we go. That's what it would look like. This pi is a leftover p orbital, right? So it just stays up there. Okay, I hope you got that. That's pretty much how the whole test is. And I feel confident. Your homework's been looking good. So best of luck.